Hello, everyone. This is Umair Durrani, and you are watching Transportation Talk. Today, we are joined by Sungyong Chung, who is going to introduce OpenCF, which is a way to benchmark car following models. So, if you work with car following models, if you develop your own, this is going to be a very interesting talk to listen to. So, I'll let Sungyong to introduce himself and then also start with his presentation. Go ahead.
Is basically a benchmark that can be used for any person who works or worked on car flying models. So I'm happy to share. And this paper is co-authored by Yanlin Zhang and Dr. Ali Reza Taleper in our group. And I am a PhD candidate at University of Illinois at Urbana-Champaign. So before I introduce OpenCF, I am briefly going to introduce about my recent works. So again, I am Songyong, and today's talk would be the OpenCF. And this paper is now accepted at ITSC 2026 for publication and for presentation. So I will have another chance to share the paper in a few months. So this OpenCF is basically a extracted curve following data set that was captured from the Waymo vehicles. So this has very high accuracy of and high fidelity of the data set, and this shows like very smooth trajectories. And what I've been doing was not only just this, I've been using curve following data set for come up with a new class of curve following model, which we name it as Markov chain curve following model. So this data set is huge, basically over 80 hours of driving. So this allowed us to come up with a pure data driven model. So this Markov chain performing model basically samples the acceleration from what was observed from the real world trajectory. And also we model the transition of the states as the Markov chain. So this surprisingly works really well compared to like the most widely used models like physics-based models. And not only on car flowing model, I've been working also on the lane changing behavior modeling. So what I used as a data set was the Waymo Open Motion data set, and this is basically the data set that is collected from the Waymo vehicles. So we extracted all the lane changing events from the data set, which would be a high fidelity trajectories. And by looking at the real world lane changing trajectories, we model the behaviors and model the evolution of the behaviors using the evolutionary game theory. And also for my most recent load, quantum game theory. So this one overcomes what the classical game theory has, and we introduce the entanglement parameter, which is in an element in the quantum game theory. And we discuss like introducing this quantum concept into modeling behaviors can model the behaviors of the real world better. So if you're interested in these studies, you can also scan the QR codes. And I am going to start introducing the OpenCF paper. So today's what we are going to discuss. So the reason we came up with this paper is because of the reproducibility crisis in car following. So basically, we currently see a lot of car following models out there, and also even recently in top tier journals, we still see car following models. But the problem here is that all the car following models use different data sets basically. So when you read the paper, some of them uses ngsim from the past papers, and recently people are starting to using like Heidi data set, Leaf data set, and also what else? Like TGC and so on. But even if so basically if you use different data set and compare different models, like papers show their numbers on like specific measures, but if you compare it with like other paper that uses different data set, it's kind of impossible to compare one with the other. And also, even if you use the same data set, we don't really have a way of doing pre-processing. So everyone does it differently. So basically, even if you use ngsim, the pre-processed data would be different. So it's hard to compare with each other. And another reason it's hard to compare is because of goodness of fitness functions and the measure of performance. So some people use, for example, RMSE of spacing, for example, as the objective function and the measure of performance, but others use different measures. So we need to discuss, our community needs to discuss which would be a good measure of performance as well, and also of course goodness of fit functions. Yeah, and also in other data sets that gives us the data set for car following modeling, some of them shows both test and training data set to the public. So basically people can overfit their models to the test set. So it is again the reproducibility crisis. So that is the reason we came up with this OpenCF. So today I'm going to introduce like what we have in the data set and how you can use it. So in the OpenCF, we have over 32,000 car following events collected from the Waymo sensors. And we do not share the test set. So basically test set is hidden, and what you can see and what we open publicly is the training data set. And this training data set, I will go over the details, and this is over 80 hours. So this is enough for modeling the car following models. And we also introduced in this paper a new evaluation metrics called geometric mean probability, and I will going to discuss that as well. And also, basically, you can train your model and you can submit the results of the trajectories that your model generated, and then the GitHub actions will automatically evaluate your model, and then it will automatically update the leaderboard on the GitHub. So I am going to share that as well. So this is the OpenCF dataset. So as I said, we extracted 32,559 car following events from the Waymo vehicles. And this not only includes like the spacing between the vehicle speed, but it also includes the acceleration data. And this is quite smooth. If you plot them, like you will see this is quite smooth. And this table shows the details of the dataset. So this has over 83 hours of driving for the training data set, and we randomly sampled 500 pairs from the data set, and which we name it as the hidden test data set. And this is something that no one can see. And we release the training pairs, which is 32,000 car following pairs. And the average duration of each car following pair would be around 10 seconds, and which ranges differently. So each of the car following pair has different length, and it can go up to around 60 seconds, 16 seconds. And this is the distribution of the follower acceleration from the training and the test data set. And the reason I'm showing this is because since we sampled 500 pairs randomly, the distribution is quite similar. So we are quite confident if you train your model with the training data set, because the test data set has the same distribution, it should work well as well.
Could you explain a bit more about the data? Does it include other vehicles? So there are cars and there are autonomous vehicles here as well, right? Are there trucks there as well?
Thank you for your question. Um, So we did not include any Waymo vehicles car followings in this data set. So basically all the followers and the leaders are human driven vehicles. And the reason we wanted to did that is because we have a lot more human following human trajectories. And the focus of this is to like fair comparison between the car following models. So basically we focus on human following human vehicles such that they will have the similar distribution. And also we sampled only the passenger vehicles, basically by length of the vehicles. So it didn't include any truck drivings as well. So this would be human passenger vehicle following human passenger vehicle in the data set. So I'll move on to the task definition and input and output. So basically what we have in the data set is the longitudinal state. So basically the position, speed, and acceleration of the leader and the follower. So I told you like the duration of the car flowing events are different by pairs, by different pairs. And for the training data set, we of course release from 0 seconds to the end of the trajectory, both the longitudinal states of both leader and the follower. And for the test data set, what we released is only the first 3 seconds of the follower history and the full sequence of the leader trajectory. And the reason we released the first 3 seconds is because there might be like LSTM type of models that want to use the previous states as the information of the input of the model. So that's why we release 3 seconds, and what we compare is from 3 seconds to the t end if the model predicts the follower trajectory closely with the ground truth. And we allow models to submit up to 6 trajectory samples for the stochastic models, and I am going to discuss a bit deeper into this measure. So for the we have the evaluation as a service. So basically you submit your model's trajectory using the CSV files and upload it into the GitHub, and it will automatically um, evaluate the metrics that we suggest in the following pages, and it will update the benchmark leaderboard as well automatically. So these are the evaluation metrics we used. Um, and we also use RMSA, but I'm not including here because that is the most widely used measures in the transportation research groups. But these measures are, so the first two measures are widely used in the automated vehicles community. So I brought these two measures because they can capture the stochasticity of the model. And we also introduced a new measure called geometric mean probability. So the mean ADE stands for minimum average displacement error. So we allow the model to subject k trajectories, and then what we are interested in is among the k trajectories, we want to find the best trajectory that is closest to the ground truth. And the reason we allow this is the following. So think of this like we think of this event, you have the leader trajectory and you are the follower. And we want to follow the leader trajectory. And even if the leader trajectory is identical, every time I follow this leader vehicle, my trajectory would be a distribution. Basically, it would be quite stochastic and it would be not random, but I'm saying this would be the would have the distribution. So in other words, what we observe from the trajectory is only the one sample among the plausible trajectories that could have happened given the leader trajectory. So if we try to fit the model to be exactly same as the observed ground truth of the follower trajectory, that the that is great for that single trajectory, but that does not can capture the distribution, the realistic behaviors of the human driving. So this measure is perfect for doing that. We can allow k trajectories, and one of them at least. So one of them should be close to ground truth. So this measure is the one that does that. And also they use this measure as well, minimum FDE, final destination error. So they don't look at the whole trajectory, they only look at the final destination and see which among the K trajectories, which one has the closest final destination to the observed ground truth. And
So, question here,
mhm,
so that I understand, for both min80 and min50, you mentioned stochasticity here, but there are
mhm,
many car following models that are deterministic. They will always give you the exact same trajectory if the parameters are not changed.
that
So
is correct.
how do these metrics work for them?
So for those metrics, basically if we said we allow up to k trajectories, k equals to 6 trajectories, and even if they submit 6 trajectories, they would be identical. So that's the property of those models, deterministic models. So
Right.
k would be 1 basically when we measure
Okay.
those metrics. But here's the thing, um, I do not believe that is unfair because that's the property that the model has, and by using deterministic models, we are saying that could capture the behavior of the human driving. So basically, that would be the something that the model is missing, the distribution of the behaviors.
Yeah, that makes sense. And one question from your previous slide was
Okay.
you mentioned that there are 3 seconds that you provide as an input.
Mm-hmm.
So, for example, if you talk about intelligent driver model, it
Mm-hmm.
will, if you're starting from zero speed, then it will apply a certain parameter like the maximum acceleration and the delta to accelerate the vehicle. So, if we already provide the 3 seconds, the initial three
Mm-hmm.
seconds of the trajectory, um, do you think that's fair to compare with what the model is generating in those first 3 seconds?
It would be fair to sorry. It would be
So, for
fair to
example, the
compare with.
IDM the IDM model would generate its own trajectory, and we have the first 3 seconds from the
Mm-hmm.
model generation, right?
Yeah.
And you're also providing the input of the 3 seconds of the follower history, right? So this is
Yeah.
already provided to the model, which means that we are going to discard the first 3 seconds that the model has generated. Am I getting it correctly, or am I wrong about this?
Um. So it is wrong. So we provide 3 seconds, but if you're using IDM, for example, it only uses the previous time step, right?
Right.
So the model wouldn't use the provided information from 0 seconds to 2.9 seconds. It will only use the last time step information to predict the next one and use that information to predict the next one and so on. So what we evaluate is from the 3 seconds to the t end. So the first 3 seconds is up to you. If you want to use it, you can use it. If you don't want to use it, you cannot use it. You can choose not to
Okay.
use it.
Okay.
Does that
So,
make sense? Mhm.
yeah, just so that I understand completely, that would mean that the IDM generated up to 2.9 seconds or 3 seconds, and we are now starting from the next time frame from IDM, and we are using the previous time step, the value that you are providing in the follower history, right? So we're not using IDM's on generated values from the previous timestamp. We're using it from the model inputs. Is that correct?
Basically, yes. So IDM
Okay.
is not going to predict anything from the first 3 seconds. That's given, and that's the ground truth. And for the remaining trajectory, we only give the leader trajectory. So model has to predict the follower state for the next time step and use that as an input for the next time step, and so on.
Got it. So I think puts an interesting question here because
Mm-hmm.
when you study IDM, it says that it is a proactive model, right? So for the first
Mm-hmm.
3 seconds, it's going to, based on the desired distance that the equation is calculating, it's going to base the acceleration on that. And so if
Mm-hmm.
the first 3 seconds are not generated by the model itself, and we are using now the input already provided to the model,
Mm-hmm.
then that proactive acceleration is not going to be used that the model was generating, right? So I think that could probably somewhat bias the model, although it's only 3 seconds. I understand it's very small. If you are predicting it for like 30 seconds, out of that 3 seconds very small, but it may still bias the model output a bit, if I'm understanding it correctly.
Um. So, in my opinion, so this is basically designed for all of the models out there for the fair comparison. And for IDM specifically, it uses the previous timestamp. And it is totally up to you if you want to use this first 3 seconds trajectory, because we have both, you will have both follower and the leader trajectory. It could be possible you can use first 3 seconds to train or fine tune the model. But
Right.
what we want is your model should generate the ground truth trajectory or the distribution of that as correctly as possible from 3 seconds to the end, which is not provided. No one knows what really happened, but we have the ground truth trajectories and the model should generate it. And that's the whole point of car flying models.
Yeah, that's a very valid point because you want it to be fair comparison with other models. Got it.
So basically, this not only allows IDM, it only also allows like data driven models because this is huge, and also this allows like LSTM type models because they need the previous time steps information. If you want to use it, you can use it, but it doesn't guarantee if you use it, the model will perform better. We don't really know. So this is like the playground for all the other models out there to see what performs the best.
Got it. Thank you.
Thank you. So moving on to the final measure. So this is what we propose here is the geometric mean probability. So when we define the state of car flowing as the speed difference, and the distance between the leader and the follower, if we define the state as that, recent paper says that the state transitions probability. Basically, if you're in state one, the probability of you being in state two in the next time step is not one. So it will be a probability stochastically. And this distribution of probability transition, state transition, what we call is the state transition probability. And let's say you have the ground truth follower trajectory. And in each time step, you will be in one of the state. And from one time step to the next time step, your state could change or you could stay in the same state. So the state transition probability of the ground truth trajectory wouldn't be one. So this is not 100%. Even for human, state transitions would be a probability less than one, and it will have distribution of those transition probabilities. And what we claim here is the transition probability distribution should be captured from the models. So the model generated trajectory should also have the distribution of state transitions, and the ground truth would also have the distribution of state transitions. And what we do here is we compare those distributions statistically to see if the model generated trajectories, state transitions are same or different, basically, from the ground truth distribution. So that's what we call, this is the measure for the capturing naturalistic driving of human drivers. So we basically try to capture all these three different types of measures. One is the one-step accuracy, which is widely used in transportation science. So one-step accuracy is basically because we provide first 3 seconds, we only look at what you predict in the first time step, basically time step at 3.1 second. So we look at those values of spacing, speed, and acceleration, and we compute the RMSE from the ground truth observed values. And these are the one-step accuracy that I talked about. And then the next is open loop accuracy. We provide 3 seconds of the follower, and we ask you to estimate the trajectory of the remaining trajectory. And we use all of those sections to compute these metrics: mean ADE that we discussed, mean FDE, and finally the collision rate. And the final metric is the geometric mean probability to see if the model generated trajectories state transition distribution is identical or not to the human driving. So these are like we provide in the paper like the well widely used models to as a baseline, and you can also see the results of these models on the website leaderboard as well, and you can compare your models with the performance of this. So the reason we have three IDMs here is because basically even if you use identical model, what you choose as the objective function, what you choose as how you optimize it. For example, genetic algorithm, or you could also use like BFGS type or like any tools out there. So even if you have the identical model, how you train it will make the difference. So this is what we showed in the paper, like the simplest ones, root mean squared error of spacing, speed, and acceleration as the objective function. And what you can see is if we set the acceleration, RMSE of acceleration as the objective function, you will see better performance in the one-step accuracy. But if you set it with spacing, it will perform better in open loop accuracies, open loop measures. So that was the trend that was observed in all the other models. And also IDM as IDM Gibbs models showed 0% collision rate because basically they are designed to do that. But full velocity difference model, Van Aren model shows some collision rate higher than 0%, but they perform better in one step and open loop measures. And for the naturalistic driving geometric probability, you will see that only three of the checked models says the distribution cannot be said to be different from the ground truth, but for the all of others, the distribution was statistically significantly different. So here's the summary of the OpenCF paper. So this is the first standardized car following benchmark with the hidden test dataset, and it automatically evaluates using the GitHub Actions. And this is a huge dataset, and we measure three-dimensional space like accuracy, safety, and naturalism behavior as well. And so this is basically ready for stochastic models as well. And one thing still on the benchmark, no model wins all three fronts simultaneously. And our community should try and like compare different models in this playground. I hope to see like which type of models, which type of objective functions, which type of tools to optimize it is the best for the car following models. Yeah, so basically that was the end of the presentation. And this is the screenshot of the leaderboard on the GitHub page. So when you go to the GitHub page, you can download the dataset. So this is saved in the Google Cloud, so you can freely download it and you can train your model and then you can submit it. Then you will be able to see your model the next day with on the benchmark.
This is great. Thank you so much for sharing your research with us, and also congratulations on the acceptance of the paper. I look forward to read it.
Thank
I
you.
have one question about the implications of what the leaderboard and the table that you showed us
Mhm.
is saying different objective functions would result in different evaluation metrics to be smaller or bigger than the others. Do you
Mhm.
think there is a need to like combine different objective functions, and a single objective function should have like multiple objectives, like for example, reducing the root mean squared of spacing as well as speed and acceleration? Or do you think there's no advantage of doing that and we should focus on what is the application? For example, if the application of the model is to to be very accurate compared to human behavior, so that you can actually see what are the surrogate safety measures and try to reproduce them from the empirical data, then the objective function should be different compared to if all you care about is that the spacing should be similar to the observed data. Do you think that would change what objective functions to use, or should there just be one?
Um, I do not have exact answer for that because all of what you said makes sense, I believe. Because like depending on what objective function we use, let's say we have to use IDM, then depending on what objective we use, the model will have different strength, of course. And yeah, so mm, That would be an interesting discussion, and of course there are a lot of papers out there, like if you combine our MSE of spacing and speed, what happens? There's a whole bunch of papers like that, and we do know like they will have different strength. But what we claim here is basically um we want to find a model that performs the best in like all three different fronts, if that's possible, because maybe the model itself is restricting from what it should be doing. And the whole point of car flowing model, I believe, is of course there could be many different usages. Is what we first did. The reason we did was to like replicate what's happening out there, and it would be better to capture everything basically, like the distribution, the spacing, or headway distribution as well. We want to that's why we always calibrate, even using vsim sumo. We have the model, but we calibrate the parameters to match what's happening out there. But maybe there could be room for improvement for another model that can capture all of this. Maybe.
Okay, great. Thank you so much again for your time. And I look forward to reading that paper as well as the other papers that you showed us at the beginning of the slides. And good luck in your dissertation defense.
Thank you very much, Amir.